In this example, we're going to start talking about derivatives as rates of change. Basically, we're going to be talking about some word problems. So just to kind of summarize a little bit what we got going on, that we have velocity, speed, acceleration, all these things have some meanings. Anything that we have this s of t is going to represent our position function. And then if we take the derivative of that, it's going to be our velocity, right? And then if we take the derivative of that, which is the second derivative of the position, so the derivative of the velocity is going to represent your acceleration equation. And then speed gets talked about from time to time because velocity is going to have direction associated to it. But if you do the absolute value of it, it's speed. So if you're going down the highway, it doesn't matter which direction you're going, you're just going 50 miles per hour, right? So velocity, though, will attach a direction to it, either a positive or a negative. So our first example is position and velocity of a patrol car. So it says, assume a police station is located along a straight east-west freeway. At noon, the patrol car leaves the station heading east. Position function of the car, here's our position function, over here to the right, gives the function or gives the location of the car in miles east when your position is, aka your y value, is greater than 0. So all of these are east of the station. And then it's west if your position is negative, right? If your y value is negative. So that little section is west of the station. All right. So, and then of the station, t hours after noon. So noon would be time 0. So describe the location of the patrol car during the first 3.5 hours of the trip, right? So basically, the car takes off and it starts moving east until we get to this spot where we're not moving east anymore, right? That distance is staying away. So let's go from 0 to 1.5. So 1.5 hours. And I'm not going to include, because then I'm going to go from 1.5 to the next spot. So each of these intervals that I'm creating, I'm going to start one of them I'm going to include and one of them I'm not. And it doesn't matter which one. So from 0 to 1.5 hours afternoon, we were going east east from station, right? And then eventually we hit a distance of 80 miles east of the station, right? And then what happened from 1.5 to 2? So from 1.5 to 2, again, I'll include the 1.5. We sat there. There was no movement. Okay, so car stopped. Patrol car stopped. Right, so that lasted for about a half an hour. Okay, and then from 2 till 3.5, from 2 to 3.5, the patrol car was heading west. West toward station. And then past station. So at that point, they were at the station. They drove right by the station, and then they kept on going to the west. Right. So, because we are heading closer to the station, which means we have to be going west. And then if we keep on going, we're getting further and further away into the negatives. And they talk about the negatives of us being west of the station. Right. So it's kind of just a basic description of what we got going on. And then the next section, next question is going to be calculate the displacement. We're going to talk about that is, and then the average velocity, which is just slope, of the car between 2 p.m. and 3:30 p.m. Right, so those times right there. So between here and here. All right, so first thing, displacement. Do a real quick, what is displacement? All right, so displacement is going to be talking about what's the total distance. All right, and that distance is going to have a direction. What is our total distance to the east, or is our total distance to the west during that period of time? Right. So if you look at the graph at this point at 2 p.m. to 3:30, we were sitting here and we went to here. So we basically went from 80 to negative 20. So if you're going from an 80 to a negative 20 at 2 and 3:30, then our displacement is a total distance. Oops. Spelling displacement, not distance. Displacement is 100, but it is a negative 100. Right, we went down. It's according to the graph, which also meant we went to the west. So our displacement is a negative 100, and that means we went, our direction matters. And if you didn't put the negative, then I would assume that we would went to the east 100. So it is 100 miles west is really what that means. All right, and then the other part of this is find the average velocity, and that average velocity really just represents slope, like the y2 minus 1 times x2 minus x1 style. And then we just need some points, right? And so if they're giving us our time increment, we need the y values associated with it, and we can figure out what our slope is. So our average velocity is going to be this right here, coordinate wise, is at 2. We're at a distance of 80. And then at 3.5, we're at a distance of negative 20. So if we do our normal y2 minus 1, so we're going to go negative 20 minus 80 divided by 3.5 minus 2. And that's going to get us a negative 100 over a 1.5. And if we throw that into the calculator, we would get a negative 66.7 miles per hour. And so since there's a negative on that, we were going to the west at a rate of 66.7 miles per hour. All right, and then last thing, at what time is the instantaneous velocity, so we're talking about a slope at a particular point, greatest as the car traveled east? All right, so traveling east is us right here. We're traveling east because we were heading away from the station. All right, so what is basically the greatest slope? We're looking for essentially the greatest positive slope. All right, so I don't know, we'll take a guess that it's somewhere between here because it kind of starts to level off here, and then it kind of hits its peak somewhere in there. So somewhere between, so at some time between 0.5 and 1.0. Somewhere between there. We would need some more information and data in order to kind of figure that out. But if we just kind of had to take a guess right now, that's what we got. All right. So that was just a beginning look at finding or talking about derivatives as rates of change and just kind of connecting some word problems. No real derivative stuff is quite happening yet. So we were just kind of analyzing some slopes and directions and connecting it to word problem.